All right, let's go ahead and take a look at this example. We're going to consider this differential equation. This is a second order. And of course, our coefficients happens to be functions, more specifically polynomials. And our XO is a -2. So we're going to find a power series solution near XO, which is -2. Before I show you how to do it, there's another example I have worked on in a separate video. Please take a look at that, and then you can try to do this problem. This is a little bit of more work than the one I have done previously. So let's dive right into it. So since we're seeking a power series solution, we know our solution form, it's going to be y equals the sum starting from 0 to infinity of a sub n x minus xo to the nth power. Here, our XO is going to be -2, so that's where I'm going to substitute right here. So our solution form would then become the sum starting from n equals 0 to infinity of a sub n x minus -2, so that'll be +2 to the power of n. So we're looking for what are the coefficient of this particular power series. So let's go ahead and write out a few terms, and then I'll show you how to do it. So if I let n equal 0, we have a sub 0, x minus x plus 2 to the 0th power. So that's just really 1. So our next term will be for n equals 1. So we will have a sub 1 times x plus 2 to the first power. The next term is for n equals 2. So you'll have a sub 2 x plus 2 to the second power, and so on. So I'm just going to go ahead and write one more term, a sub 3 x plus 2 to the third power. So our goal is to figure out these coefficient right here. Now, at the end, we are going to fill in our coefficient in terms of a sub 0 and a sub 1, and we'll modify a sub 2 and 3 based off those coefficients. So let's go ahead and do that. So we need to find its first derivative, second derivative, and that's what we're going to sub in right here. Let's compute the first derivative of y. In closed form, our first derivative would be the sum. When you take the first derivative of this list of terms, the first term will disappear, so our sum will start at 1. So you'll have the first derivative starting at n equals 1 to infinity of n times a sub n x plus 2 to the power of n minus 1. Now, you could write out the terms, but that's not so important. Let's keep it in this form. And hopefully, I hope you can see that here we're using the power rule of differentiation. We bring down the power and subtract 1 from the power. That's how I got this. And the second derivative would be, now again, using the power rule, the sum will start at 2 to infinity of n times n minus 1, a sub n, x to the power x plus 2 to the power of n minus 2. So that will be the term for the second derivative. Now that's what we're going to plug into our summation. So we will have our x times y double prime. So when you substitute these expressions, we're going to substitute these infinite sum. So this is the first derivative right here. This is the second derivative. We're going to sub that in right here. So let's check this out, how it looks like. So we will have our differential equation will look like x times y double prime. So that will be the sum starting from n equals 2 to infinity of n times n minus 1, a sub n, x plus 2 to the power of n minus 2. So that's the first term. Now for the second term here, just to save some time, or at least not to get things a little crazy, I'm going to go ahead and distribute this term out. So we can write this as x squared y prime minus 4y prime. So that's what I'm going to plug in right now. So we'll have x squared. So be plus x squared times y prime. Y prime is this sum right here. So this would be the sum starting from n equals 1 to infinity of n times a sub n x plus 2 to the power of n minus 1 minus the 4. So here I have 4 times y prime. So we'll have -4 times exactly the same sum. So starting from 1 to infinity of n times a sub n x plus 2 to the power of n minus 1, everything equals to 0. All right, so we got some clearing to do. So I hope you can see what I did. I made the substitution. with my y prime and y double prime of our infinite sum. Now, here, before we simplify algebraically, we're going to have to do a quick substitution, because if you try to move this x inside the summation and combine it with this, we cannot because of the x plus 2 term. So we're going to make a quick substitution. This is one way to do it. There are probably plenty other ways that you can approach this problem. I like it by substitution. So I'm going to go ahead and make the following substitution. Let t, introducing a different variable, replace x plus 2. So that means x is really t minus 2. So we're going to make this substitution before we proceed. So we're going to change all of these terms into t variable. So all of these. All right, so here's how it's going to look like. So the first term we have x, well, x is t minus 2. So we have t minus 2 times the sum starting from n equals 2 to infinity of n times n minus 1, a sub n, and x plus 2 is t, so this is t to the power of n minus 2. Plus, now the second term, we're replacing x with t minus 2, so we'll have t minus 2 squared, since it's x squared in the original, times the infinite sum starting from 1 to infinity, n times a sub n, x plus 2, that's t to the power of n minus 1. And then the last term we have minus 4 times the sum starting from 1 to infinity of n times a sub n, x plus 2, that's t, so we have t to the power of n minus 1, everything equals to 0. Okay, I hope you can see what I'm doing. Now we're going to go ahead and expand. So here I'm going to distribute the infinite sum to t and to 2. Now for this one, this is a bit of work because we need to expand this before we can start distributing the sum. So I'm just going to work on this sum. So pay attention right here. So t squared minus t minus 2 squared, well, that's really t squared minus 4t plus 4. So I have this times my infinite sum starting from 1 to infinity of n times a sub n, t to the power of n minus 1. And now I'm going to go ahead and distribute my sum to each of these terms. So again, pay attention only to the middle term here. So if I distribute, here's what I'm going to get. I have t squared times the infinite sum, and starting from 1 to infinity of n times a sub n, t to the power of n minus 1. For the second term, we have minus 4t times the sum from 1 to infinity of n times a sub n, t to the n minus 1. And the last term, we get plus 4 times the infinite sum, starting from 1 to infinity of n a sub n, t to the power of n minus 1. So all of that is substituting. So all of these guys are substituting this piece right here. I hope you can see that. So I'm going to go ahead and now I'll take care of these guys right here, distribute the sum to the t and to the 2. And then here, if you notice, this sum and this sum, they're exactly identical with opposite sign. So they actually cancel each other. So I'm going to go ahead and cancel that. So, so as you can see, the so this infinite sum and this sum will cancel out. So let's pull everything together. So what we have left is this one. I'm going to go ahead and distribute. And then we have this one, this one. Yeah, those are the one we have left. All right, so let's go ahead and write that out. So first sum, so we have t times the infinite sum, starting from 1 to infinity of n times n minus 1, a sub n, t to the power of n minus 2. And then I distribute it to the negative 2. So that gives me minus 2 times the sum from 1. I'm sorry, this sum should start at 2. Little typo here. So starting at 2 to infinity of n times n minus 1, a sub n, t to the power of n minus 2. And I'm going to rewrite these guys right here because those are the ones that survived. So just to save some time, I'm going to go ahead and just copy them. So this will be our next term. That will be added right here. And then the last term is the negative 4 times the infinite sum. So I'm going to go ahead and copy this as well. So the last term in our equation is going to be this, minus 4 times that, everything equal to 0. So remember, the last two pieces cancel each other out. Okay, so I hope you got to this far as well. Now let's start moving the variables inside the sum. So I'm going to go ahead and move this inside, combine it with that. I'm going to move the 2 inside here, and then t squared inside here, combine it with that, and negative 4t again, move it inside here. So as I move them inside, I have the first summation starting from 2 to infinity of n times n minus 1, a sub n t. Now here we can combine their powers. So the first t has a power of 1, then we have t to the power of n minus 2. That was simply t to the power of n minus 1. Okay, minus, now I push the 2 inside. You don't have to, but I think I want to do that. And starts from 2 to infinity of 2 times n plus 1, a sub n, t to the power of n minus 2, because there is no t in front of it, plus, now the third summation, we push the 2 inside. We have the sum starting at 1 to infinity of n times a sub n, t to the power of n plus 1, as you combine the powers of t. And the last one, almost there, we get minus the sum starting from 1 to infinity of 4 and a sub n t. Now here again, I can combine this has a power of 1, this is a power n minus 1. That'll give us t to the power of n. Everything equals to 0. All right, I hope you can see that. So let's give ourselves some room. All right. Okay, now here's when we're going to try to have all of the sums start in the same place. But before we do that, I want to have all the t's with the same power. So we're going to introduce a dummy variable so that all of our t have same power. So for the first one, I'm going to introduce, let's use k to replace n minus 1, which means n is going to be k plus 1. For the second summation, I'm going to use k is equal to n minus 2, so n is equal to k plus 2. For the third sum, we're going to use k is equal to n plus 1, which means n is k minus 1. And the last one, k is n. So we're just introducing a dummy variable, so all of our t contain same power. Okay, so now we have the sum. If n starts at 2, that means if k is n minus 1, k will start at 1. So once I do that, I see my sum for this one, k starts at 1. And then as n goes to infinity, k will go to infinity. N is k plus 1. And then n minus 1 is k times a sub k plus 1 times t to the power of k. All right, wonderful. And then minus the second one, here our k is going to start at 0 to infinity. 2 times k, k is n minus 2, so 2 times n would be k plus 2. And then n plus 1, well, that's going to be k plus 1. A sub n is k plus 2, and then t to the k. The third summation, again, following that substitution, now if n starts at 1, k will start at, looks like here k is going to start at, if n is 1, k is going to start at 2. And then all the way to infinity, n is k minus 1. And then we can sub in for a sub k. So a sub n would be k minus 1, t to the k. And the last summation, we have a minus. So it'll be minus the sum. So n starts at 1, k will also start at 1. So we're just replacing each n with k. Also go to infinity for k times a sub k, t to the power of k equals to 0. All right, now that looks pretty good. So now all of our t has same power. That's what we wanted. Now we can start shifting our indices. So you look at the one that has the higher k value, the starting higher k value. So it looks like this one has the highest k value. That means I want to start this one at 2, this one at 2, and this one at 2, so that they can all start at the same place for k. So that means we need to write out k equals 1 for the first. For the second summation, we're going to write out 2 terms until it starts at 2 for k. And the third one, we don't. We keep it as letting it start at k equals 2. But the last one, we're going to write out 1 term. Okay, so for the first summation, we write out k equals 1. So that's going to give you, now these terms, they're not so needed, but I'm going to write it out anyway. So if k equals 1, you're going to have 2 times 1 times a sub 2 times t to the 1. So now this one can start at 2. So let's hold on to that. For the second one, we write out 2 terms, k equals 0 and 1. So we have minus 2 times k equals 0, so 2 times 2 times 1, a sub 2 times t to the 0, so that's going to disappear, minus, now I'm again writing out k equals 1 for this guy. So if k equals 1, you have 2 times 1 plus 2, that's 3, and then 1 plus 1, that's 2, a sub 2 plus 1, that's 3, k to the 1 power, and now this can also start at 2. The third one we don't write out because it's already starting at 2. This one we write out 1 term when k equals 1. So we have minus 4 times 1 times a sub 1 t to the 1 plus, now we can group all of the sum into a single summation. So we'll write plus the sum starting from k equals 2 to infinity. They're all starting at the same place of, so I'm going to write out all of the coefficients of k. So this one with the negative sign, and then this one, and I also factor out t to the k. So here's where I'm going to get. So I'm going to get k plus 1 times k, a sub k plus 1. Again, I'm factoring out t to the k, minus 2 times k plus 2, k plus 1, a sub k plus 2. That's the second. And the third one, we got plus k minus 1 times a sub k minus 1. And the last one, minus 4 k a sub k. Everything times t to the k equals to 0. All right, so we have this giant equation. So this is what going to give us our recursion formula. Now, these terms are not so needed. You can equate their coefficient to the right side, and you'll see that you'll get those coefficients from this formula anyway. So you can almost ignore them. So for now, these guys right here, you can almost ignore these. They're not so needed because you're going to get them from the recursion formula anyway. But if you really want to work it out, you can use those to find your coefficient. I believe you can find a sub 2 and a sub 1 from here because that's what they appear. Okay, so I'm going to go ahead and start with my coefficient right here of t sub k. So I'm going to set this equal to 0. So you'll have k plus 1 times k times a sub k plus 1 minus 2 times k plus 2 times k plus 1 times a sub k plus 2 plus k minus 1 times a sub k minus 1 minus 4 times k times a sub k equals to 0. So this is how you're going to get your coefficients. So to do this, we're going to solve for the highest subscript, which is this one. So just a little bit of algebra. So you'll have your a sub k plus 2 is equal to positive 4k times a sub k minus k minus 1 times a sub k minus 1, and then minus k plus 1 times k times a sub k plus 1. And we're going to divide that by these coefficients right here to isolate a sub k plus 2. So you'll have negative 2 times k plus 2 times k plus 1. All right, this will give you all of your coefficients. So I'm going to go, so we know our solution is going to be term of a sub 0 and a sub 1. That means if we get other coefficients, we're going to rewrite them in terms of these two. Since we only have second order, you have 2 unknown coefficients. So let's start with k equals 0. If k equals 0, we get a sub 2. So a sub 2, it's going to be, if I plug in k equals 0, you'll see all the numerator, it's going to be 0, except for this one. This one has a negative subscript, so we know those are going to be 0. So a sub 2 will be 0. All right, so we got another coefficient. K equals 1, you're going to get a sub 3. So a sub 3, as you work it out, you'll see that this is going to be 4 times a sub 1 minus 0 minus 1 times 2 times a sub 2 all over negative 2 times 3 times 2. And we know a sub 2 is 0, so this is 0. So this is really negative 1/3 a sub 1. All right, so that's a nice coefficient. Let's go for one more. So we got a sub 3. I'm going to go for one more for k equals to 2. That will give me my coefficient a sub 4. So that's going to be in k equals 2 into this recursion formula. We have 4 times k is 2. So this is 4 times 2 times a sub 2. And that minus a sub 1 minus 2 times 3 times a sub 3 all over. You'll get negative 2 times 4 times 3. And by further simplification, this will give us negative, so we know this is also 0. Okay, so this is going to give us negative a sub 1 over negative 24 plus 1 over 3 a sub 3. Okay, simplifying a little further. And then this will simplify to, let me see. Well, we can replace a sub 3. So we know a sub 3 is this value. So I'm going to go ahead and sub that in here. So then this will give me a sub 1 over 24 minus 1 over 9 a sub 1. And then you can combine their coefficient. So this is really just negative 5 over 72 of a sub 1. All right, that's our coefficient a sub 4. Again, you want them in terms of a sub 0 and a sub 1. Now we're ready to write out this solution. So we're almost there. Let's go back. So we know our solution looks like this. Now I'm going to substitute my coefficients and we're done. So so here's our solution, right? And we're going to sub in. So a0 and a sub 1, they're going to stay as it is. But a sub 2, we're going to substitute that for 0. So we know this is going to be 0. Then a sub 3, we found that to be negative 1/3 of a sub 1. So this is negative 1/3 of a sub 1. So I did find one more coefficient. I'm going to go ahead and write that as well. So plus, no, that happened to be negative. So we know our next solution is going to be plus a sub 4. So we know this is plus a sub 4, x plus 2 to the 4th power, and then keep going, right? So I'm going to go ahead and replace a sub 4 with its coefficient I found. So this would be minus 5 over 72 of a sub 1. So I'll give ourselves a little room. Minus 5 over 72 times a sub 1. All right, and then keep going. So this is our solution. You can clear things up a little, regroup them in terms of a sub 0 and a sub 1. But the idea is explained, so I hope you got to the same answer as me. All right, yeah, that's it for this problem. I hope you enjoyed. Take care, everyone.